but in order to keep this relatively on schedule, I'm going to go ahead and start. And so I won't mind at all if you just keep right on eating while I talk. My name is Bob Houston. I'm the Special Assistant Director for Structures at Langley Research Center. I know the welcome was supposed to be given by our Center Director, Pete Peterson. However, last week he just was appointed Associate Administrator for Office of Aeronautics and Space Technology in NASA headquarters, and he can't be here today, so I'm his substitute, and I send you his regrets that he can't be here, but his welcome that you can. I'm going to give you a little background on Langley Research Center's history, and then I'm going to give you a brief history of rotorcraft research at Langley. First, though, I'd like to thank a number of people who had a part in setting this up. Please don't stop eating if you have a little bit more to go. Colonel Terry from the Quad A, Colonel Gordon from the Captain Gordon. I just promoted him. Captain Gordon from the Quad A, Commander Daly, and Lieutenant Commander Zamansky, NHA. Joy French from the AHS. And several people here from the NASA Public Affairs Office, Cam Martin, Ann Suit, and Gary Price. I'd also like to give a special thanks to John Klein, who's in the Army Aerostructures Directorate, who took care of essentially all of the logistics. And if you haven't talked to him, it's because you didn't bring something in or arrange something. John, where are you? John? Stand up. Give John a hand, will you please? I'd also like to thank the crew that brought in Huey number 23. It's out there on the flight line today. It was, I understand it was built in 1962, and that may be older than some of the people that are here. With that, let me go ahead and get started a little bit of Langley's history. The purpose of Langley Research Center is to perform innovative aeronautical research and relevant to the national needs and agency goals, and to transfer these research results to the user community in a timely manner, and to provide development support to the government agencies, industry, and other NASA centers. I wanted to give you some insight into what the center itself is responsible for. It is an old center. It was founded in 1917. It was the first civil aeronautical research laboratory in the U.S. It has about 3,000 civil servants. The facilities that are around here would cost in excess of $1.5 billion to replace. We have an active, ongoing facility program. We do aeronautics and space research. In fact, roughly 60% of our work is in aeronautics. We have a full range of disciplines, and we have about 40% of our work in space disciplines and atmospheric science. The history of Langley really starts back with NACA. The National Advisory Committee for Aeronautics was formed in 1915, and they acquired the property here at Langley. First built the first wind tunnel and began making a number of steps of progress that have reflected in aeronautical history. The NACA cowling, de-icing, X1 came out of Langley. First transonic tunnel was built at Langley. The area rule was a concept that was generated by one of our researchers and showed a great deal of progress as time went on. In 1958, NASA was formed, and it took over the NACA facilities across the country, as well as some Navy and Army facilities, and then took on a role. Mercury Lunar Orbiter was a Langley project where we took the first close-up pictures of the moon. We landed a lander on Viking in 1976. X-15 was a concept that was worked on here. That supercritical wing, that same gentleman who came up with the area rule, applied that concept to the 767 when Boeing applied it. We've been working in shuttle, space structures. The original concept of the space station came out of Langley, though it has been changed quite a bit if you keep track of things like that. We've been heavily involved in composite technology, scramjet work, and in fact, a concept of aerospace plane depends upon that kind of work at this time. We have, in addition to that, a wide variety of aeronautical research disciplines at Langley, all the way from aeronautics to acoustics, propulsion integration, controls, flight management areas, the material structures, aeroelasticity. In the space arena, we're working on atmospheric sciences heavily, theoretical modeling of the atmosphere, the work on the ozone that you may read about in the papers, and now if you flew in, you saw this. You saw this facility right here. Most of the choppers are parked right along this ramp right here, and all of these facilities that you're looking at are Langley, NASA Langley Research facilities. If you're familiar with the Air Force side, you'll recognize there's some strange buildings over there. There are several wind tunnels that belong to us that go back to the 30s. This tunnel here was built the year I was born, and that was 1931. Next to it is the Transonic Dynamics Tunnel. There's an 8-foot supersonic tunnel and several other facilities that were used in the early research, some of which have been turned over to the Air Force. But we still maintain a presence in the east area with these nationally important facilities, and I'll show you some of this. Some of you will visit those facilities yet this afternoon. We operate a number of tunnels. I think there's about 40 wind tunnels, subsonic, transonic, supersonic facilities that provide the aeronautics capabilities for performance, stability control, as well as propulsion integration and high-speed propulsion concepts. Hypersonic facilities. One of the things that's unique about Langley is we have our own fabrication shops. In fact, we just brought a satellite back from orbit here a while back, LDEF. That satellite was built in our facilities. We have the very latest in central scientific computers. We're working in the basic instrumentation sciences, laser sensors, this sort of thing, electronic instrumentation. And I threw back in the structures and materials area because these are some of the more unique areas that we have: working structural dynamics, jet noise, test capability in structures and materials, landing dynamics, and you're going to have a short talk after I'm through about that. Now let me turn to the early Langley rotorcraft research. I tried to gloss over the rotorcraft work, but I wanted to tell you that rotorcraft's been an effort here at Langley since 1922. If you go back and look at some of the reports that were published at that time, you'll find a couple studies. One that was done with the propeller in one of the rotors, aimed at looking at the effects of forward flight on the propeller moments, and a configuration that looks strangely like a command servo tab. I don't think that had anything to do with the concept that Charlie Command came up with later, but you'll notice this rotor blade does have a little tab out here on the end. In 1931, the PCA-2 autogyro was certified and began sales throughout the United States. I don't remember exactly how many, maybe 40 or 50 of them were built. NACA chose to buy one, and it became one of several autogyro research efforts that went on in that particular time frame. I meant to show you these close-ups of these other two, and let me jump on to the next one. The PCA-2, you can probably see it a little bit better here, but it does say NACA 44. This aircraft was used here to understand the stability control as well as the performance. And as it went into the wind tunnel, they were able to obtain test data from that to develop initial performance charts that and processed for evaluating performance that has led to more modern performance evaluations of today. About 1938, a hingeless rotor autogyro was built by Burke Wilford. About 1972, he came by here one day, and I had a chance to talk to him. I asked him to autograph that picture. I happened to be having worked a little bit on some hingeless rotor work at that time, and he told me the history of this aircraft. Langley was given this aircraft from the Navy. You see prominently on here, U.S. Navy. And we did some work on the application of hingeless rotors. The unique thing about this aircraft was it had cyclic pitch. Autogyros do not have cyclic pitch. And we did quite a bit of evaluation of that aircraft at that time, and with some interesting results that led to studies later on. In 1944, the Sikorsky R-4 became one of our research aircraft. One of the people who's sitting out here, Jack Reeder, sitting right there, took over a flight test of this aircraft and began to learn a lot of things about the stability control of the aircraft. But in that time, we also went back and looked at the performance of the aircraft and tested it in the 30 by 60 wind tunnel. You'll see that this is looks a little bit cluttered, but you see a man up here. There's some ladders and things like this available. And again, it extended the performance work that was done on the autogyro back in the early 30s. Let me say that the 30 by 60 wind tunnel was used for a lot of various kinds of results. Here's one that was just looking at a single rotor. This is a fairly large size rotor. Here's a little smaller rotor that was tested in there. And just to put me in proper perspective, this is me in case you don't recognize me. That was a couple years ago. And we were also looking at some convertible rotors. This happened to be an airplane which carried the Hughes Monker as rotor wing. And I realize it's a rather poor picture, but it's the only one I could find to show you some of the kind of things that we were looking at. That is a convertible airplane to convertible from a helicopter to an airplane flight. The concepts that we looked at that time didn't prove practical, but we were looking at some concepts that might not have finally developed. If you walked over from the hangar, you probably saw the child care center for our employees. There's this funny looking little building down here with a little silver dome on top. And that's the old wheel tower that was built in the 40s to understand better the hover characteristics of rotors. We also looked at some strange rotors. This happened to be called the rag rotor. It's really two little lightweight poles with a stabilizing fin, and the attempt was to make a sail rotor or a rag rotor. And if we could ever stop the luffing, it might have been successful. They had a figure of merit about 0.5, so it wasn't all that bad. But that was one of the interesting things that we've done on the tower. There's a whole series of rotors that were tested like that. We also looked at some of the strange vehicles. Here, for example, is believe it or not, that was the loser of the LOH competition that we received here at Langley. Put a wing on it, tried to do a few experiments with it at that time. Here's an H-13 where we put a hingeless rotor on that particular aircraft and flew it, looked at the stability control and some of the loads problems. The XH-51, which was a Lockheed hingeless rotor, gyro controlled, and you begin to see an effort to understand hingeless rotors and the dynamics and the loads associated with those. Sometimes we looked at some strange blade tips. Here happens to be an OG tip. We also looked at a variety of different airfoils on what we call around here the White Cobra. This aircraft was eventually returned to the Army, and I understand it's been converted to the very latest model Cobra. I'd like to switch a little bit and talk about some of the evolutions of flight dynamic research that we had. Starting in the early 50s, we were looking at mods of aircraft to affect stability. I don't have the picture that shows the actual mod, but here's an HO3S, and we put some stabilizers back here, a couple horizontal stabilizers in here to decreased the dynamic the download and provided increased stability. I think Jack had a part in all that too, I should point out. As time went on, we looked at more advanced concepts, variable stability aircraft, and incidentally, it's a good point to point out that sometimes our aircraft came to a sad end. On the last flight of the HO-3S, it was intended to be the last flight. We ran into ground resonance, and the aircraft ended up on its side. There's Jack. He looks about the same as he does right now. I don't think Jack was flying that day. It was Bob Champagne and who? Well, anyway, but I wanted to make a point, and that is that we were heavily involved in dynamic instability investigations. The analysis people were developing the ground resonance equations and the solution for that much prior to this particular accident, and that kind of dynamic work has gone on, including understanding blade dynamics, understanding airframe and fuselage dynamics. But I thought that I wanted to show that particular aircraft and its eventual demise at the same time. But we began to look at variable stability aircraft, and we took the HO-3S, a joint program that we did with the Army. Excuse me, the YHC-1A, I'm sorry. This is the prototype of the CH-46, the YHC-1A, and we installed analog and digital computers in it to drive electrical input servo systems and begin to examine flight dynamics. Eventually, that particular aircraft was used in an Autoland by 1972, and I know that some of the Navy people were making automatic hovers at that time, but we were making an automatic deceleration to a point and a hover and a vertical letdown, all with onboard, at that time, analog equipment. And we found ourselves needing to look at the display research and understand better the display. This led to the use of the YHC-1B, which is a prototype of the CH-47. It seems like we always get these old leftover aircraft here, but they're cheap. We provided flight display input, cockpit displays, did tracking with lasers and radar, and we're able to develop a system that, whoops, we just lost, I'm sorry, back up one, will you please? I think I lost the chart. No, I must have lost the chart. One thing I would like to say before I leave this is that one of the things we did with this system, we eventually turned this aircraft over to the Ames Research Center, and while we were demonstrating this for a number of people, including outside companies and everything else, we took our center director up there and we put him in the cockpit and we let him make a blind landing. First time he'd ever had his hands on the controls in his life. And from a piloting standpoint, we were able to give him flight director commands that he could follow, and he was quite successful in doing that. I think that sort of signifies the kind of control and display research that we were doing at that time. And but when this particular effort was terminated, some of the people that were working that began to work on a new focus. They began to work on transport displays, and using an aircraft called the Vault program, and where we had an aft flight deck that looked like this, where all of the displays were glass cockpits. And if you happen to go out in a 757, a 767 at this time, you'll find that those aircraft have these glass cockpits. The impetus to do that, and they were probably the first in the United States, the impetus to do that was this particular program, which really came out of the rotorcraft program. Incidentally, Jack was head of that group too. I didn't mean to point on Jack all the time, but since Jack's here, I can't help but point out that his personal contribution through this has had a great deal of to make our history what it is. In this particular time, and I wanted to show this just to say that we didn't do everything in the rotary wing field. We were also looking at some of the other vertical lift concepts, the XC-142 and the P-1127, the predecessor of the AV-8 type aircraft. These aircraft were those that were built for the tripartite squadron that was the British, Americans, and the Germans well before the AV-8B came. We did stability control research and operating problems research in that, and essentially the same kind of group of people did that. A key event occurred in 1970. We signed an agreement with the Army Aviation Systems Command for an Army group here and to do related aviation research and development efforts. That meant that we actually have an Army detachment here, and I introduced John a few minutes ago. John is a member of that group. They're integrated into our research, doing about 60 people total altogether here at the center, and we do a lot of co-work on Army as well as NASA activities in these arenas. Now let me just talk a little bit about another project that got started, one that was close to my heart. Concept of a high-speed research vehicle was established about the time of this joint program, and the concept of this aircraft we looked at in the wind tunnel. We developed the aerodynamics, the dynamics of that aircraft, and eventually built these two. These are called the RSRA. They were built under contract to Sikorsky. They eventually flew in more than one configuration. The helicopter configuration, the compound configuration, and after it was delivered to the Ames Research Center in another configuration where the only visible rotor is on the tail rotor. That was in preparation for work on the X-wing configuration, which is not shown on here. Now I want to turn to some of the facilities. The 14 by 22 foot subsonic wind tunnel we're not going to be able to visit today, but it has been used for a lot of wind tunnel experiments. I think you'll recognize most of these vehicles, with a couple exceptions. Maybe this one was a concept. We have a couple generic helicopter rotor drive systems, and put different kind of fuselages on that drive system to examine some of the aerodynamic characteristics of that. Sometimes we change the configuration, like we were looking at a V-tail on a Cobra at one time. It never actually got built, but we had a design and looked like that this would solve several problems that we could have if it had been evaluated in flight. As other aircraft come along, we find that we're solving some specific problem. For example, the AHIP had some tail problems. We were looking at some of the issues in using the 30 by 60 tunnel and been tested in the 14 by 22. Some near field flow configuration work. But we're also looking ahead. If you happen to fly an Apache, you won't recognize this blade because it hasn't been built yet. But that's an advanced blade for the AH-64. Conceived of, developed here at Langley. Hopefully will be used one time. I'd like to also point out that on the Apache, we've even looked at things like longbow. This little dome up here has some interesting little characteristics, and we've had to go look at it with some laser sheets to see the kind of flow that actually occurs around it. And as you look at the flow, as you get up close to this particular picture, you have a little bit of trouble, but you start looking in closer, you begin to see there's some very interesting flow dynamics involved around this. And it's this kind of detailed examination that allows us to make significant effects on the design as things go on. One of the studies that happened here at Langley was an effect at anti-torque assistance. And they found, for example, that with some strakes stuck on the tail boom, that they could reduce the pedal required under certain operating conditions. And it's been applied to several aircraft, including our own. I also point out that there's also a number in Europe that have picked up on this, and it's apparently all generated based on the research that was done in the 14 by 22. We are working and developing codes to predict the very complicated flow theory. including the pressure distribution on fuselages, and trying to verify these codes and have good success at this time. Like I said, a little bit about the transonic dynamics tunnel. Some of you will be visiting that tunnel. There is a hover rig in a building behind. This is the transonic dynamics tunnel. There's another building behind it which houses this hover rig. There is a model in there. This is what the model looks like. It's about this particular size. We've done a number of things in the transonic dynamics tunnel. This happens to be an advanced Black Hawk rotor that have been experimented with, and we're going in with some additional blade configurations shortly there. One of the things that we looked at in about 1970s, early 70s, was higher harmonic control to reduce vibration. We actually applied this to an OH-6 helicopter, and that particular helicopter had a very significant reduction in vibration, and it has so far it's never been applied in production, but I think that somewhere in the future you're going to see higher harmonic control. Basically, it's on this particular aircraft, it was 4 per rev blade pitch inputs that would reduce the vibration. I would point out also that we've been looking at tilt rotor configurations. Is there one more? Yeah, here it is. Back in the late 60s and early 70s, we worked on the dynamic problems of the tilt rotor with a number of configurations, eventually ending up with a configuration which looks like the XV-15. And that aircraft was built and flown by a joint program with NASA Ames and the Army. And eventually the V-22, or the JVX at that particular time, was tested in our transonic dynamics tunnel. One little aside, this particular picture was used in a presentation to an assistant secretary of the Army, and somebody got scolded for posing pictures with pretty girls. She was a test engineer, I should point that out. Yes, she was. I alluded to the dynamics work that we've been doing, and we have a dynamics program where we were looking at the dynamics of airframes in toto, including coupled rotor airframe analysis. And we've had a series of studies that actually have literally taken a Cobra apart and shook it almost part by part to try to assemble the components of that particular problem, try to understand it better. And as part of the finite element modeling work, we work with the companies in Pacific test to validate the kind of modeling, structural dynamic modeling that goes on. Here, for example, is this difficult component picture. You see that Cobra almost totally disassembled, but shook in each particular element to try to understand the interfaces between all those doors, the transmission mounts, which happens to be off at this particular time, the engine mounts, try to better understand why some of our best predictions don't work as good as they really ought to. Let me say a little bit about noise. Langley has the agency's role in noise research, and a major part of that, or a significant part of that, has always been helicopter research. We use a number of facilities to do tests, but we do fundamental work, including interior noise, active noise control. And over the years in the noise research, we've had to go sometimes to other facilities to do tests. Here happens to be using the Boeing Vertol test, but we also have to go out in the field, and that means acquiring a very major stream of data, and we've actually had to build a data trailer to handle these things, go out in the field and make flyover measurements over ground arrays to gather the kind of data that we can characterize all the characteristics of the noise. These are a couple of the configurations that we've looked at and are studying, trying to validate the noise prediction schemes. That means that we have to go out and do tracking of an aircraft. This particular aircraft has a couple of interesting additions. This very large trash can at the back to get rid of the engine noise, because we wanted to separate the parts of the noise, as well as happen to have 4 blades, which is not a normal configuration for that particular model of OH-6. We also are very interested in the tilt rotor, and we've looked at that particular aircraft and expect to, if the Navy will permit us, to get data on the V-22, because we have an ulterior motive there in terms of development of tilt rotor technology overall. Let me say a little bit about our crash facility. The Impact Dynamics Research, we have a gantry back here where we've been looking at the effects of adverse impact. We swing an airplane down and impact onto either a runway surface or dirt. And we've been looking at those kinds of problems with rotorcraft. And the Army, nearly all of these were done in cooperation with the Army. The people at Fort Eustis developed the crash-worthy requirements. And a large part of their external work was done with us, where we looked at crashing 47s. Here's the loser of the the attack helicopter competition, a couple of the ACAP aircraft. But fundamental to this is understanding the dynamics of this to the structure itself. Here's two pictures here that show a crash. This is actually just at contact, and this is 0.05 seconds later. I just thought I'd show you that to give you some idea where things start. And here is a crash of the ACAP. We have a composite material laboratory. While we don't focus much directly on composite materials directly for rotorcraft, we do run the complete range of efforts that are applicable all the way across the board, all the way from the pot chemistry, where we develop matrix resins, scale them up, try to pregnate them with fabric, do the associated construction of a composite, and then characterize that. As part of our program in the materials area, we've actually been flying, again, it was a joint program with the Army, flight service components. And actually, it turns out that we get a lot more flight hours on the civil aircraft than you would on the military, because their flight experience, except possibility of Desert Storm, runs a lot higher than ours. So these test programs have gone on for about 10 years to give us confidence in the use of composites. Just switching subjects a little bit, structural laboratory. Here again, we're in a number of different concepts, and we're looking at application for a civil tilt rotor of composite fuselage and wing, and that has a payoff, we think, in application to the future. And let me just close with a couple comments about where we think we're going. This just sort of gives you an insight. Way back when I showed you that stop rotor picture, maybe that stop rotor will come up again. We're looking at, still looking at things like stop stowed rotors. Here, for example, is a very old picture of a cooperative program with Bell where we were looking at folding a rotor. We just recently completed a cooperative program with Douglas, where we were looking at some McDonnell Douglas helicopters, where we're also looking at some folded rotors. What all this may lead to is a second generation advanced tilt rotor transport technology, and you see a lot of this work would be done here, and up in here is Langley's area of expertise. And where we think the payoff is that advanced civil tilt rotor transport may be a viable alternative to relieve airport capacity problems. If you've ever been into New York, San Francisco, a number of the airports actually have capacity problems, and about 40% of their traffic is commuter airplanes. And we believe that if we replace the commuter airplanes that now use the runway space with V2L aircraft like tilt rotors, that we could enhance the capacity of the world, of the United States particularly, but of the world's airports. And with that, I was almost on time. I didn't quite finish. Let me introduce John Tanner. John is going to tell you a little bit about the track and the crash facility. He'll say a little bit more than I did. John?
need this button? Yeah. All right. Get all cussed up here. You probably noticed on your agenda that you were supposed to, after my little 10-minute pitch here at lunchtime, go down and see a run on our aircraft landing dynamics facility. Unfortunately, we're not going to be able to do that today, and I'll share with you the reason for that in a little bit. But what I'm going to do instead, I'm going to do, hopefully the next best thing is I've got a couple of videos that I'm going to present. One will talk specifically about our aircraft landing dynamics facility, and the other one will talk about some of the crash work we've done in association with the Army with helicopters. The branch that does this type of work is the Landing and Impact Dynamics branch, and this is sort of a montage which gives you an idea of the kind of things that we do. Up in the upper left, that's the kind of thing we try to avoid, obviously, with our research. When we do get into that kind of a problem, and that particular airplane that you see burning there was a NASA Convair 880, I believe it was. But it had an aborted takeoff on the runway, and a tire failed, then another tire failed, and then pieces of tire and wheel went through the wing, set the wing on fire, and the aircraft was a total loss along with all the instrumentation on board. So that's the kind of thing we try to avoid. Fortunately, all 19 people on that aircraft got out. The facility that I'm going to talk about has done a lot of work for the space shuttle. And then the second facility that I'll talk about this afternoon that Mr. Houston's already shown you is our Impact Dynamics Research Facility. Well, this is a photograph of the catapult phase of our aircraft landing dynamics facility. We refer to it as LDEF. It's basically a half-mile long test track with a test carriage, which is about, well, it rides on rails which are 30 feet apart, and the highest point on the carriage is about it's about 28 feet, and it's about 60 feet long, just to give you some indication there of the size. It weighs 115,000 pounds, and we use high-pressure water to catapult it up to speeds. Now, the video that I'm going to show you here in just a second shows you how this facility operates, and it's about a 3.5-minute video, and I'll just let it narrate itself, and then I'll have a few words after that before I show you some of the research that has been accomplished on that facility. So if we can have the video, first video.
The Langley Research Center Aircraft Landing Dynamics Facility is a unique national resource designed to test a wide variety of landing gear systems and components economically and safely. The 110,000-pound carriage is accelerated to speeds up to 260 miles per hour in less than 2 seconds, and then coasts on the remainder of the half-mile track. Landing gear test articles are hydraulically loaded onto the test runway, which can be varied to simulate any runway in the world. 3 large air storage tanks are pressurized to over 3,000 pounds per square inch and are connected to the top of an L-shaped vessel containing 26,000 gallons of water. During a launch, a specially designed spherical valve unseals and opens quickly to allow an 18-inch diameter jet of water to push the carriage down the track. The water jet exits the valve at 2/3 the speed of sound and produces a thrust of over 2 million pounds, developing an acceleration of 20 Gs on the carriage.
I hear that mumble. That is 20 Gs.
A bucket mounted on the rear of the carriage turns the water jet through 180 degrees to extract as much energy as possible from the jet. Extreme uploads generated during this process are reacted through a series of hold-down rails. During a maximum effort launch, approximately 11,000 gallons of water are expended in a second and a half. As the high-speed shutter of the valve is closed, the back end of the water jet is disrupted, while the water remaining in the coherent slug continues to propel the carriage. This real-time view shows the path of a test article at a speed of 200 miles per hour. Virtually any aircraft landing gear can be tested under controlled and safe conditions. Here, an F-4 fighter aircraft main landing gear touches down at a sink speed of 17 feet per second. Landings like this are common aboard aircraft carriers. When greater than expected wear occurred on shuttle orbiter main gear tires landing at the Kennedy Space Center, tests at this facility identified the touchdown and spin-up dynamics of the tire.
You see all the rubber coming off there.
A unique use of aircraft arresting gear engines brings the carriage to a stop after a test. 5 sets of water-filled tubs connected by nylon tapes and steel cables are designed to use turbines to churn the water and dissipate the carriage energy as heat. This simple system is efficient and reliable. The cost to run a test at the facility consists of the water used and the electricity to replace the water in the L-shaped vessel, for a total of about $15. The Aircraft Landing Dynamics facility will continue to provide the aircraft industry in this country with data necessary to permit safe, all-weather aircraft takeoff and landing operations.
Okay. I need to correct one number there. That $15 is based on 1985 money. It's now up to about $20 to $25. But you see, that's still a pretty reasonable price to pay. Now, just think in terms of what we're dealing with here. 2.2 million pounds of thrust on a 115,000-pound carriage, 0 to, if I put it in miles per hour, it's 0 to 263 miles an hour in 400 feet. That's about a third the distance you have in a quarter of a mile. I guarantee it'll beat anything you'll ever find on the drag strip. And it is unfortunate that you're not going to be able to see a run today, but if you're ever back when we're running, everybody is always invited out. It is always a good show, even if we're not running at our maximum speeds. I'd like to spend a few minutes and talk about some of the research that's underway currently or has been done in the last 6 years since this facility became operational with this high-speed capability. First of all, on this slide, we're looking at cornering characteristics of nose gear tire for a DC-9 aircraft. And really the unique thing here is that we're looking at both a standard bias ply aircraft tire, which is the data when the aqua, and then superimposed on that is data from a radial tire. Now, you drive radial tires on your car all the time and have been doing it for a number of years, but radial tires is a new thing in the aircraft industry, and we're putting together a national database on a number of tire sizes where we're contemplating replacing the standard bias ply with the radial belted design. A radial tire offers a big improvement in weight, maybe as much as a 20% weight reduction, and so the airliners are going to just love it. What we're concerned with, though, is determining that, in fact, the performance of these radial tires doesn't interfere with other landing gear functions, such things as the steering capability or the anti-skid braking dynamics. In this particular slide, we're looking at the coefficient of friction as a function of yaw or steer angle, and you can see that, and we're looking at a range of vertical loads applied to the tire from 3,000 pounds, where we have the high data, to about 8,000 pounds, where you see there is a reduction in the cornering characteristics. But essentially, both tires perform essentially the same way there, and so at least for this particular application, it looks like radial tires will have no problem being introduced into the aircraft fleet. The main purpose for going with the, I think there should be a couple more slides there before we get to that one. There we go. The main reason for going with the high-speed capability, the facility itself became operational in 1955 with a maximum speed then of about 110 knots. And that was sufficient at that day and time for most of the work that we had in mind, because it was only the military aircraft that were jets at that time, and so landing speeds were generally 100 knots or below for most of the commercial airplanes anyway. But about 1958, you know, the Boeing 707s and the McDonnell Douglas DC-8s came online, and all of a sudden the landing speed started going up to about 130, 135 knots. And so we were slower than the landing speeds, and that was interfering with our testing capability. Then with the idea of the space shuttle coming along, we decided we really needed to upgrade the facility. So in 1985, we increased our speed from 110 knots to the present 220 knots. And the very first thing we started looking at were shuttle landing gear issues. And this just shows one of the more recent shuttle landings down at Kennedy Space Center. We've done a tremendous amount of work in the last 6 years looking at ways of improving the tremendous tire wear that we're seeing on the shuttle. That seems to be one of the critical issues. As it turns out, the shuttle aerodynamically has a crosswind limit of about 20 knots. But because of tire wear issues coming in on the runway down at Kennedy, our crosswind limit just from tire wear issues alone is down to about 13 knots. And so we've had to do a lot of work. In fact, we've done work on the runway itself, modified the runway, made it a lot smoother than it was originally, still retaining enough surface roughness in the runway to counter hydroplaning effects when that runway is wet. We've also modeled the friction and wear characteristics of the tire, both the nose and the main gear tire, and put those models on the simulators that the astronauts train on, so that when they actually go up and fly, I'm talking about the commander and the pilot, they actually go through many, many hours of simulator training where they go through the landing and rollout. And we also put into our test program cases where we purposely landed with the tires flat and watched the tire destroy itself, and then watch the wheel destroy itself, and then once the wheel destroys itself, just observe what happens when you slide out on the axle or the brake housing, and put all this information together and included that in the simulator so that they actually train for some catastrophic landing gear failure modes. The most recent shuttle effort that we've been involved in is modifying the tire itself. At 220 knots, when you touch down on the runway down at Kennedy Space Center, you're putting about 10,000 horsepower into each tire to spin it up. And so that's where our wear issue really comes about. On the left here, I show the cross section of the baseline shuttle tire, and it's basically 16 nylon plies thick, and then there's an inner liner here, and then the tread rubber is on the outside down here, and you can see a groove depth. This is 1/10 of an inch of groove. It's only about a third the rubber that you would have on your car tires when they're brand new, and that's because of the high-speed requirement. And it's an all-natural rubber tread. That's the standard military rubber blend or rubber compound that's used, natural rubber, because it runs cooler. But it wears very rapidly. And in fact, here's what happens. When we spin up on the modified Kennedy runway surface now, we go through about 2/3 of the tread depth. And I'm showing a plot here of tire wear as a function of side energy. Now, side energy here is just an indication of steering effort, and it could come about by fighting a crosswind or putting a steering maneuver like an S-turn down the runway. But basically, if you look out here at 2.5 million foot-pounds of energy, that would correspond to what the pilot would have to do to counter a 15-knot crosswind. And you can see that with the baseline tire, he's right at the limit, the wear limit for the tire. If you go beyond this red point, you're really subject to having the tire fail, and it would fail very quickly. The modified tire that we've done research on was actually developed based on a suggestion that was made at Langley, and we put a little more rubber in the tread area, but the main thing is we changed the compound from all natural rubber to a mixture of natural and synthetic rubber. The rest of the carcass, the plies, and the inner liner is exactly the same, and in fact you can manufacture the modified tire in the same mold, so it's a very cheap fix. But based on the testing of the modified tire, which we just completed about 2 months ago, we get about a 300% improvement in wear overall. By that I mean, in order to get into the first chord layer being shown, it takes us almost 8 million foot-pounds of energy as compared to about 1 million or 1.5 million foot-pounds of energy. 20-knot crosswind would correspond somewhere between 4 and 5 million foot-pounds of energy, and you can see that this tire can easily handle the crosswinds that the shuttle was originally designed for. This modified tire will be flying probably on STS-50, which is probably going to be about 8 months from now. So when you hear that on the news, you'll know that some of that work was done here at Langley. Well, Mr. Houston's already shown you a picture of our Impact Dynamics Research Facility. What he didn't tell you is that this started out life as a Lunar Landing Research Facility. It was originally built in the early 1960s to simulate lunar gravity. And what was done to use a series of cables to support a mock-up of the lunar landing module, 5/6 of the weight being supported by the cables, the other 1/6 supported by the standard engines that were going to be used to actually land on the moon. And so all of the lunar crews that actually landed on the moon did a lot of training on this facility. After the Apollo program ended in 1972, there wasn't a great deal of need to continue looking at 1/6G kind of experiments, and so people were wondering what in the world to do. Well, in the meantime, we did one other experiment, and that was the Viking lander that landed on the surface of Mars. They did a lot of landing dynamics simulating the gravity on Mars on this facility, but from the middle 1970s on, it's been used primarily as a crash test facility, and we've crashed something like 35 or 37 aircraft and helicopters. In addition to the full-scale crash test, we also get involved in looking at the structure itself. The idea is, how do you improve your chances of surviving in the unlikely event of a crash? Now, the Army has been extremely interested in crash-worthy designs for their helicopters for a number of years. And as Mr. Houston's already indicated, we have two Army researchers that are assigned to the branch full-time to do research primarily on rotorcraft. Dr. Karen Jackson and Dr. Richard Boitnott. I know Karen is here. I think Richard might be here in the audience too. But they work with us, and they work primarily the kinds of issues that I'm sharing with you now. What we're looking at here is the effect of floor location on failure behavior of a composite fuselage. I guess that's the other thing I should mention, that our research in the last 2 or 3 years is primarily oriented towards composite constructions, because that's the wave of the future, we think. That's where if you start looking at advanced helicopters, certainly on the NASA side, the high-speed civil transport, you're going to see a lot of composite materials. And there are a lot of issues associated with crashworthiness that we have to iron out if we're going to have the same kind of crashworthy designs with composites that we currently enjoy with our metal airframes. Up here in the upper left, you can see, if we look at a typical frame in some sort of an aircraft, and this could be an airliner, a helicopter, or a general aviation aircraft, you'll have at some point in here, you'll have a floor beam where your passengers will sit underneath here. In an airliner, of course, this is where your baggage goes. In the case of a helicopter or general aviation, you generally have a floor location which is much closer to the bottom of the frame, as indicated here. And that has a large bearing on what happens under impacts associated with crashes. Up here, if we look at the failure loads associated with impact work, and look how this varies according to the arc length, we can see that as we start, if we were to have some sort of some fictitious point at the top of the circle here, this would be our low point here, and then the 180-degree point, which is a typical airline application. You can see that there's a linear variation in the failure load. It goes up as our location of our floor descends towards the bottom of the frame. And that, you think that might be good, but actually it isn't, because what you're trying to do is limit the loads going into the airframe during a crash impulse. We're also looking at typical strains associated with those crash pulses. A lot of this work is being done with very expensive finite element technology, but closed form solutions also give us the same answers. And basically, you can see when we go from the 180-degree floor location, which gives us this big sort of gull wing approach, to the 60-degree location, typical of what we might see with a rotorcraft, you can see that there is a compression of the strain curve, but basically the failures are going to occur at the same points. They always occur at the ground contact point, which is here, and also on plus or minus on either side, usually somewhere associated where you see the peaks in the strain curves there. Since helicopters, by virtue of their design, do not give you a lot of room to put crushable structure, then of course that makes it very critical that you understand the concepts associated with crash dynamics. And for a number of years, our researchers, such as Drs. Jackson and Voigtnot, and some of the other folks in the branch have been working helicopter crash tests. And I have a video now that runs about 9 minutes. Unfortunately, it's not narrated, so you'll have to still listen to me. But I'll run that now. We'll talk about some of the things that we have done over the years. All of that I'm going to show you today are again rotorcraft testing that's been done at our Impact Dynamics Research Facility. First time through, we're looking at a CH-47 helicopter crash test. This was made several years ago. The vertical velocity at impact was, I believe, 42 feet per second. And you can see it does get messed up. On this particular program was a way of suppressing fuel leaks. In other words, there was a bladder, a fuel bladder on board, and that bladder survived this 42 foot per second drop intact, and that was awfully good news. Here you can see from a different angle. Those flashes you see are associated, I believe, with photography associated with the crash itself. Makes my back sort of watch that, you know. Okay. And there's the aftermath. Now this was the YH-63, which was the loser in the competition for the attack helicopter. And you can see we don't treat our test articles very gingerly. Observe what happens to the landing gear here. Of course, the landing gear is designed to absorb about 50% of the crash impulse. And look what happens as it starts to fail. You can see the hydraulic fluid shooting out the top there. That's an indication that the landing gear has sacrificed itself so that the pilots can survive. So maybe you ought to go kiss a landing gear. It's rather impressive, isn't it? This is what you look like in a crash. Those of you that fly. Ooh. One of the things that the Army has been interested in some years is finding ways to eliminate the accidents wherever possible. And one of the hard things you have to deal with is when you're flying a particular mission profile where you're flying close to the ground, wire strikes become a real big issue. And so we've done a lot of work supporting Fort Eustis and doing some swing tests here where we just swing the aircraft. This happens to be an Apache again, and now there's several scenes here. Probably goes on longer than need be, but I think you'll get the point here. We have communications or a telephone cable stretched across 2 poles, and we swing into it, and we have they test various kinds of wire cutters, various locations, and we set up a test so that these cables ride up and over the top of the cab, go down below the cab, as you'll see in this sequence. And I'll just let the film talk for itself here. Here's what it looks like from the cockpit. It's a little bit scary. What I didn't show you was a test that we made with a 086, yeah, the 086, it cut itself in half by doing this. So, you know, this is a dangerous thing. I would not recommend that you go out and try this, by the way. This is a case where the cable's going underneath now. And the cutter's doing its job. Basically what we had is we had a steel cable that was the structural cable, and then the communications wire was run around that. That's fairly typical of what you see in the real world. We were looking at speeds of about 60 miles an hour at the impact point with the cable. We got a flyer on the cable. It's pretty hard to see here. I think we have just a couple more scenes like this, and then we'll go into the all composite aircraft testing. We did. I think we have just a couple more scenes like this, and then we'll go into the all composite aircraft testing. We did. See some dynamics when it finally lets go there. Again, it was a fairly exhaustive test program looking at various impact locations on the airframe to make sure that the wire would slide up or down and get into the wire cutters. This is the build version of the all-composite aircraft, and it was the first one that we tested. And again, I believe this was 1988 when we ran these tests. I believe this was August of '88. All composite. There are stroking seats on board. I believe this seat stroked quite a lot. We generally do not reuse our equipment. And this is the Sikorsky version of the Advanced Composite Airframe program. And it was tested at slightly different, under slightly different impact conditions, but still they're both around 34 feet per second vertical velocities, I believe. It's a rather severe test for crash worthiness, but I believe the folks that were doing the work were fairly well pleased with what they saw. We also do tests where we're looking at things that are on board helicopters. In this case, we're looking at basically a bomb box, something that's carrying shells, and the question is, what happens if you have a catastrophic crash? So we drop this from the full height of our 240-foot gantry to get 100 foot per second velocities at impact, and you'll notice that the shell of the helicopter fuselage was extremely in poor shape after the test, but the box itself, or the container itself, survived very well. Okay, and I believe that's the end of the video. Just a couple slides here to finish up to talk about what we're doing today and in the future. I don't know how many of you recognize this, but this happens to be the fuselage of the Learfan, which was the first, supposedly the first all-composite aircraft. Bill Lear, the last project he had underway when he passed away some years ago, his wife took over the company, but unfortunately, after getting a couple of prototypes flying, the company went bankrupt. We inherited a couple of the airframes. Well, we actually bought them at a very cheap price, and all composite airframes are pretty hard to come by, especially when you find out that we're going to be crashing them. But in fact, we have two of these airframes, and we're modifying the designs on these slightly so that we can look at what sort of crash-worthy features you want put into the airframe itself. And we'll be doing crash tests with this particular specimen and its sister probably in about another 2 years. Maybe 1 year for one test, and then about 6 months before the second test. And this last slide that I'm sharing with you this afternoon just gives you kind of an indication of some of the work that we do for other folks. This happens to be a crew capsule for an F-111 fighter bomber. And you're probably aware of this, but in case you aren't, you know, when the aircraft gets into problems, you don't use ejection seats in this aircraft. The whole capsule separates from the aircraft and comes down on a parachute. But unfortunately, there have been a fair number of injuries associated with impacting the ground here. And so the Air Force is interested in reducing these injuries as much as possible. And so we've been doing some dynamic testing looking at a airbag type of system to attenuate those impact loads. And in fact, we are just finishing up tomorrow. Hopefully we will complete the last test in this particular series. There have been something like 14 tests run in this series, and that's the reason we're not able to run the track today. It takes all of our manpower to actually run a full-scale crash test like you're seeing here. But anyway, that's what we do for a living here. Okay.
Thank you, John. Well, I hope you got a little insight into what we do here at Langley, and some of us find it sort of fun One of the things that you'll find interesting about Langley is NACA, Langley Memorial Research Laboratory, goes back to 1917 when they started to build here. Building, you'll see the variable density tunnel, which actually put Langley on the map. It was capable of up to 5 atmospheres. It was driven by an external engine. You'll see as you walk outside how they got into it. Since it went up to 5 atmospheres, they had to remove the end plate of it, put the airfoil inside it, and the engineers actually stood on the outside looking through portholes, reading scales and balances from the outside and recording the data from that point in time. It was delivered from Newport News Shipbuilding and Dry Dock Yard back in 1921 out here at Langley. So the history is pretty rich here. Now for the very interesting part, we're going to break up and go into tours. Now, if you look at your little name tag, you'll have either a dot on it or nothing or a black bullet. What that's doing, we're splitting you up into 6 groups to ride the 6 buses, and that's going to put an equal amount of people on each bus. So it was just sort of randomly done to put the same number of people on each bus. Each bus will have a sign in the window. The first one out there, I believe, is black all the way to the right or the west end. And the last one is red if the order is black, blue, yellow, and green. And white and red are to the left side of the building as you walk out. The tours will go to all different areas of Langley, but they'll all converge back at the hangar at about 1500 or a little bit after 3 o'clock. And then we can play musical buses and get back on your own bus and you can get
In 1976, X-15 was a concept that was worked on here. That supercritical wing, that same gentleman who came up with the area rule, applied that concept to the 767 when Boeing applied it. We've been working shuttle, space structures. The original concept of the space station came out of Langley, though it has been changed quite a bit if you keep track of things like that. We've been heavily involved in composite technology, scramjet work, and in fact, a concept of aerospace plane depends upon that kind of work at this time. We have, in addition to that, a wide variety of aeronautical research disciplines at Langley, all the way from aeronautics to acoustics, propulsion integration, controls, flight management areas, the material structures, aeroelasticity. In the space arena, we're working on atmospheric sciences heavily, theoretical modeling of the atmosphere, the work on the ozone that you may read about in the papers, and now if you flew in, you saw this. You saw this facility right here. Most of the choppers are parked right along this ramp right here. And all of these facilities that you're looking at are Langley, NASA Langley Research facilities. If you're familiar with the Air Force side, you'll recognize there's some strange buildings over there. There are several wind tunnels that belong to us that go back to the 30s. This tunnel here was built the year I was born, and that was 1931. Next to it is the Transonic Dynamics Tunnel. There's an 8-foot supersonic tunnel and several other facilities that were used in the early research, some of which have been turned over to the Air Force. But we still maintain a presence in the east area with these nationally important facilities, and I'll show you some of this. Some of you will visit those facilities yet this afternoon. We operate a number of tunnels. I think there's about 40 wind tunnels, subsonic, transonic, supersonic facilities that provide the aeronautics capabilities for performance, stability control, as well as propulsion. But in order to keep this relatively on schedule, I'm going to go ahead and start. And so I won't mind at all if you just keep right on eating while I talk. My name is Bob Houston. I'm the Special Assistant Director for Structures at Langley Research Center. I know the welcome was supposed to be given by our Center Director, Pete Peterson. However, last week he just was appointed Associate Administrator for Office of Aeronautics and Space Technology in NASA headquarters, and he can't be here today, so I'm his substitute, and I send you his regrets that he can't be here, but his welcome that you can. I'm going to give you a little background on Langley Research Center's history, and then I'm going to give you a brief history of rotorcraft research at Langley. First, though, I'd like to thank a number of people who had a part in setting this up. Please don't stop eating if you have a little bit more to go. Colonel Terry from the Quad A, Colonel Gordon from the Captain Gordon, I just promoted him. Captain Gordon from the Quad A, Commander Daly, and Lieutenant Commander Zamansky, NHA. Joy French from the AHS, and several people here from the NASA Public Affairs Office, Cam Martin, Ann Suit, and Gary Price. I'd also like to give a special thanks to John Klein, who's in the Army Aerostructures Directorate, who took care of essentially all of the logistics, and if you haven't talked to him, it's because you didn't bring something in or arrange something. John, where are you? John? Stand up. Give John a hand, will you please? I'd also like to thank the crew that brought in Huey number 23. It's out there on the flight line today. It was, I understand, it was built in 1962, and that may be older than some of the people that are here. It was used here to understand the stability control as well as the performance. And as it went into the wind tunnel, they were able to obtain test data from that to develop initial performance charts that and a process for evaluating performance that has led to more modern performance evaluations of today. In about 1938, a hingeless rotor autogyro was built by Burke Wilford. About 1972, he came by here one day, and I had a chance to talk to him. I asked him to autograph that picture. I happened to be having worked a little bit on some hingeless rotor work at that time, and he told me the history of this aircraft. Langley was given this aircraft from the Navy. You see prominently on here, U.S. Navy. And we did some work on the application of hingeless rotors. The unique thing about this aircraft was it had cyclic pitch. Autogyros do not have cyclic pitch. And we did quite a bit of evaluation of that aircraft at that time, and with some interesting results that led to studies later on. In 1944, the Sikorsky R-4 became one of our research aircraft. One of the people who's sitting out here, Jack Reeder, sitting right there, took over a flight test of this aircraft and began to learn a lot of things about the stability control of the aircraft. But in that time, we also went back and looked at the performance of the aircraft and tested it in the 30 by 60 wind tunnel. You'll see that this is looks a little bit cluttered, but you see a man up here. There's some ladders and things like this available. And again, it extended the performance work that was done on the autogyro back in the early 30s. Let me say that in the 30 by 60 wind tunnel was used for a lot of various kinds of results. Here's one that was just looking at a single rotor. This is a fairly large size rotor. Here's a little smaller rotor that was tested in there. And just to put me in proper perspective, this is me in case you don't recognize me. Integration and high-speed propulsion concepts. Hypersonic facilities. One of the things that's unique about Langley is we have our own fabrication shops. In fact, we just brought a satellite back from orbit here a while back, LDEF. That satellite was built in our facilities. We have the very latest in Central Scientific Computers. We're working in the basic instrumentation sciences, laser sensors, this sort of thing, electronic instrumentation. And I threw back in the structures and materials area here because these are some of the more unique areas that we have: working structural dynamics, jet noise, test capability in structures and materials, landing dynamics, and you're going to have a short talk after I'm through about that. Now let me turn to the early Langley rotorcraft research. I tried to gloss over the rotorcraft work, but I wanted to tell you that rotorcraft's been an effort here at Langley since 1922. If you go back and look at some of the reports that were published at that time, you'll find a couple studies, one that was done with the propeller in one of the rotors, aimed at looking at the effects of forward flight on the propeller moments, and a configuration that looks strangely like a command servo tab. I don't think that had anything to do with the concept that Charlie Command came up with later, but you'll notice this rotor blade does have a little tab out here on the end. In 1931, the PCA-2 autogyro was certified and began sales throughout the United States. I don't remember exactly how many, maybe 40 or 50 of them were built. NACA chose to buy one, and it became one of several autogyro research efforts that went on in that particular time frame. I meant to show you these close-ups of these other two, and let me jump on to the next one. The PCA-2, you can probably see it a little bit better here, but it does say NACA 44. This aircraft, with that, let me go ahead and get started a little bit of Langley's history. The purpose of Langley Research Center is to perform innovative aeronautical research relevant to the national needs and agency goals, and to transfer these research results to the user community in a timely manner, and to provide development support to the government agencies, industry, and other NASA centers. I wanted to give you some insight into what the center itself is responsible for. It is an old center. It was founded in 1917. It was the first civil aeronautical research laboratory in the U.S. It has about 3,000 civil servants. The facilities that are around here would cost in excess of $1.5 billion to replace. We have an active, ongoing facility program. We do aeronautics and space research. In fact, roughly 60% of our work is in aeronautics. We have a full range of disciplines, and we have about 40% of our work in space disciplines and atmospheric science. The history of Langley really starts back with NACA. The National Advisory Committee for Aeronautics was formed in 1915, and they acquired the property here at Langley, first built the first wind tunnel, and began making a number of steps of progress that have reflected in aeronautical history. The NACA cowling, de-icing, X1 came out of Langley. First transonic tunnel was built at Langley. The area rule was a concept that was generated by one of our researchers and showed a great deal of progress as time went on. In 1958, NASA was formed, and it took over the NACA facilities across the country, as well as some Navy and Army facilities, and then took on a role. Mercury Lunar Orbiter was a Langley project where we took the first close-up pictures of the moon. We landed a lander on Viking.